very international background since his PhD in Italy, since his early study in Italy, and then he went to Australian National University for his PhD, and then did a research in several different institutions in Australia, and then Europe, back to Australia, then back to Europe. And currently he's a researcher at ETH. So with that, I will give the rest time for Andrea to talk about Kimberlite story. So Andrea, could you still keep the video on so that the audience could hear you, could look at you when you are speaking, so that's easier to catch up. And I'm going to turn my video off to ensure the quality. Okay, and we're going to record the talk, I think, according to our previous conversation. Since this paper is published, I think we could to advocate. Okay, with that, Andrea.
So is it all good? I mean, can you see both my screen as well as my picture, my image? Well, my video. I guess, I mean, if I don't see it, I guess, yes. Okay, cool, thanks. Continue. All right. So, I mean, my talk today, the title is a little bit different from that of the paper, because this was, let's say, part of a larger seminar, and today I'm focusing more on what was presented in the paper. So the talk is called "The Kimberlite's Journey Across Scales," because I'm going to move at a different depth of the Earth, lithosphere, and also deeper by using Kimberlites. Before starting, I should thank the Australian Research Council to fund my previous research activities. I guess you can see my my cursor here, as well as my former host at the University of Melbourne and Macquarie University, and also the Swiss National Foundation to fund in my current stage of activities. And as you can see there, I'm currently based at the ETH. Okay. All right. So, well, this is the paper, I guess. So I can probably, well, of course, I also quite a big thank to all my co-authors for supporting various stages and various activities that then resulted in this contribution. So I'll start with a broad introduction about kimberlites, why do we care about them, why they're important, what do we know about them, what we don't know, and then I will the central part of this talk will focus on this paper, and lastly I will touch a little bit about upon what primary kimberlite melts potentially are, or at least what I think they are, and also I will briefly talk about some ways to move forward.
Okay, Andrea, could you use full screen? I think now we see two very small screens on it.
Let me see what could be the problem.
Because it's the same screen on both. Yeah, okay. Now it's actually even better.
You know what? I just let's disconnect the other screen and just use a single one.
Yeah, I think even you keep it like this, it's better than what it was.
Yeah, is it? Can you still?
Okay, yeah. Okay, perfect.
Oh, good. Okay, cool. Yeah, I have two screen here. This is why I probably was messing up with Zoom. So I guess the main reason why most of you might know kimberlites is because they are the main host of terrestrial diamonds, with all the major diamond mines essentially being hosted in kimberlites, so primary kimberlite deposits. And I mean, while you might think the diamonds are just well-marketed pieces of carbon, as I also partly do think, actually, when you are there staring at large quantities of diamonds sitting all together, then I mean, that's pretty exciting. Down here, you can see me and John Woodhead visiting the diamond personal collection of John Gurney, who recently passed away. And up here is myself and Jock Robbie, a former De Beers geologist, in a diamond sorting plant, that we are directly looking at those trays full of diamonds. So it was quite a spectacular experience, I must admit. And the other fundamental reason, perhaps more relevant for us as why we care about kimberlites, is that they represent the deepest melts that we can find at Earth's surface. And in other words, they can provide perhaps unique information about the composition of and evolution of the deep Earth. Okay. Sorry, sometimes it gets stuck. So kimberlites occur on every continent of the world, as you can see in the map up here, where in the salmon-colored fields represent continental shields. Kimberlites are reported as red diamonds, and the yellow diamonds represent kimberlites that were either formerly or are currently mined for diamonds. Kimberlites were in place mostly during the last 600–700 million years, with a few spikes earlier on, as you can see in the chart down here on the left-hand side. And potentially some kimberlites were older than 2.1 billion years, even though these reports are quite contentious. Overall, we have about 6,500 kimberlites reported in the world so far. Less than 1,000 of them contain appreciable quantities of diamonds, that is at least 1 carat per 100 ton. And actually only 70 are diamond mines. And so now I'll start with our journey with kimberlites in the upper crust. So this is how kimberlites actually look like. These are the emplacement mechanisms of kimberlites in the upper crust. They're either pipes, which are carrot-shaped diatremes that can be as deep as about 2 or maximum 3 kilometers. And this is an aerial view of the mine pit of the Letlhakane diamond mine in Botswana. Or otherwise, kimberlites occur as dikes, or more rarely as sills, which can be associated with pipes, or in other cases just occur as swarms of dike, not associated with other intrusive features. The important thing of kimberlites is that pipe, even when they're in place as pipes, and most of the times they do not really occur as a single unit. So do not imagine just a single phase of volcanic activity generating the pipe, but the internal structure of the pipe can be very complex and reflect multiple intrusive or extrusive events. And this is quite important because these also reflect multiple pulses of kimberlites ascending through the mantle. So this will become important later in this talk. So kimberlites, while kimberlites might be well known because they host diamonds, something to keep in mind is that diamonds only occur at the sub-part per million level. And things like this fat guy, which is called Letseni Larona, just above 1,100 carats, that is about 400 grams. These are very rare diamonds. Okay, this was sold at something like $53 million in the market, which really tells you why it's quite helpful to have to find them, to have a few kimberlites around the world, such as Karowe, where this diamond was found in Botswana, that can produce those sort of diamonds. So beyond diamonds, kimberlites are quite complex rocks that host abundant crustal fragments, as well as abundant mantle fragments, such as this nice garnet xenocryst down here. This is an eclogite microxenolith, and of course diamonds. Olivine is the main constituent of kimberlites, roughly occurring on about 50% in volume. But I'll come back to olivine later because it's really the central focus of this talk. Kimberlites are also very enriched in volatiles, both CO2 and water. For CO2, it's quite easy to see. There is a lot of carbonates, mostly calcites and secondarily dolomite in kimberlites, as you can see in these pictures. In this case, all the interstitial material is indeed calcites. Water is mostly stored in serpentine, but here things are a little bit more contentious. So serpentine typically replaces olivine in kimberlites, as you can see here, but also occur as a ground mass constituent. And for these reasons, for decades, serpentine has been considered a true magmatic phase in kimberlite, which I guess sounds a little bit awkward, especially if you are a metamorphic petrologist, for example. And I mean, this honestly also sounded awkward to me, especially after I looked a little bit deeper into the literature, especially when I was first studying kimberlites. So here on the left-hand side, I have copied and pasted a very nice charts from this study of Richard Brooker and co-authors, where on the x-axis you have water, in either kimberlite rocks or in their experimental melts, and this is the pressure conditions for their experiments. Their experiments, essentially, they tried to squeeze in as much water as they could inside potential kimberlite melt composition at very low pressure. Okay, so these are upper crustal pressure. So these are the pressure of kimberlite melt intrusion in the upper crust. Whereas here you have typical water contents, roughly, typically above 4 or 5%. These experiments show you in gray the solubility of water, the maximum solubility of water in kimberlites, meaning that in kimberlite rocks, you have much more water of what can actually be housed in a kimberlite melt. In other words, this is clearly an excess of water in kimberlite rocks, an excess of water that cannot derive from the kimberlite melt itself. And this can also be demonstrated by looking at the oxygen isotopes of serpentine. In this chart, we have oxygen isotopes on the left-hand side, on the y-axis versus temperature. On the x-axis, these are the composition measured so far for oxygen isotopes in serpentine, and these are the temperature of serpentine formation. Essentially, this gray box represents the composition and temperature conditions of formation for serpentine. This curve up here, where labeled magmatic fluid, gives us the composition that serpentine should have at these conditions, at these temperature conditions. And as you can see, this curve doesn't intersect the condition of serpentine in kimberlite. In simple words, we need another source of water with a lower oxygen isotopy composition to form serpentine of this composition. And this water is probably groundwater. So where does this water come from? This is a relatively old idea of C. Sparks, who essentially suggested that when kimberlites in place in the upper crust, hydrothermal circuits develop whereby we have exchange of fluids between the kimberlite melts and rock and the wall rocks. Ultimately, what you get is that a nice fresh kimberlite like this, if it's not isolated from this process, turn into a serpentine-rich kimberlite, such as what you can see here on the right-hand side. Importantly, this also has a fundamental effect, and not just in terms of olivine serpentinization, but also in terms of ground mass composition. So what Steve Sparks and his co-authors in his paper showed, White is one of his former students, is that serpentine, the abundance of serpentine in kimberlite here on the y-axis, is inversely correlated with the abundance of calcite and phlogopite here on the x-axis. That means that the formation of serpentine, the introduction of external water in kimberlites, has a massive effect not just on water, but also on silica, magnesium, calcium, CO2, every major element. And this remains one of the fundamental issues that we have to understand the composition of kimberlite melts, both upon emplacement and deeper in the mantle. So now I'll switch back to olivine before, so that I can cover essentially the focus of this talk. So olivine, as I mentioned before, is the most abundant phase in fresh kimberlites, occur in all sorts of size and shapes. Some of them evidently look like this big guy up here, look like mantle-derived xenocrest. Others are nicely hewidral grains that you would probably call phenocrest. However, the definition of phenocrest and xenocrest in kimberlites, especially for olivine, is quite labile. Let's say it's quite weak. Any olivine grain, as you can see from these backscatter electron images, includes both a core and a rim of different composition. It's quite clear from this difference in the brightness in of backscatter electrons. This difference is even more clear if we look at typical charts of olivine compositions, magnesium versus nickel, magnesium on the x-axis, nickel on the y-axis. These are two different localities, Udachnaya in Russia and Kimberley in South Africa. You can clearly see that the cores show quite variable composition, especially in terms of magnesium number, whereas the rims, and this is typical for kimberlites all around the world, in any kimberlite typically show a fairly restricted range in magnesium number, where the magnesium number is simply an indication of magnesium over iron ratio. So going from the cores towards the edge of the grains, the magnesium number remains roughly constant, whereas nickel decrease. And with nickel decreasing, calcium increase and manganese increase. Okay. The other fundamental observation is that when the core is sufficiently small, the rim tend to develop a very nice hewidral shape for the whole grain, thus giving that shape typical of phenocryst. Finally, the third observation to keep in mind is that the olivine rims typically host inclusions of magmatic phases that occur in the groundmass of kimberlites, chromites, ilmenites, and more rarely perovskites, phlogopites, and apatites. So if we combine all these observations together, I think you would all conclude, as everyone else has done so far, that the rims have a magmatic origin. But we can move a step forward, and we can now compare the magnesium number of the olivine rims here on the x-axis with some indication, some quantitative indication of the composition of the kimberlite groundmass. So in this case, we have used phlogopite plus oxide minerals concentrations. So in the charts on the left-hand side, you can see the results for 4 different pipes in the same cluster of kimberlites in Finland called Kavikuopio. And you can see that there is quite a nice correlation between the composition of the groundmass and the magnesium number or the iron magnesium ratio of the olivine rims. And we've done a similar exercise using a bunch of kimberlites from around the world, from Canada, Brazil, and South Africa. And you can see that this correlation seemed to hold. In other words, it would seem that the magnesium number of the olivine rims, which is relatively constant in every kimberlite, it represents quite a good proxy for the composition of kimberlite melt upon emplacement in the upper crust. But what about the cores? To talk about the cores, we have to continue our journey a little bit deeper and move to the lithospheric mantle. So these are 2 plots of the composition of olivine cores in representative kimberlites from around the world, for which abundant data exist. So on the left-hand side, we have magnesium number versus nickel. On the right-hand side, magnesium number versus manganese. The composition of these olivine cores, which are reported as circles, are compared to the composition of olivine granular peridotites, the yellow field. These are your typical mantle xenoliths that you find in kimberlites or other rocks from cratonic environments. Then the blue field indicate the composition of olivine in sheared peridotites, which are essentially metasomatized rocks where the metasomatic agent was probably some precursor kimberlite melt. And the gray field indicated the composition of olivine megacrystal. Again, olivine megacrystal are interpreted to be the product of kimberlite metasomatism preceding the eruption of kimberlites at surface. So the fundamental observation and simple observation here is that the vast majority of olivine core compositions nicely overlap with the composition of olivine in other mantle lithologies entrained by kimberlites, and therefore that occur in the lithospheric mantle sampled by kimberlites from all around the world. These localities include Canada, Russia, Greenland, Zimbabwe, and South Africa. There are a few exceptions, but more than 90% of the compositions for olivine cores overlap with olivine mantle rocks. The second observation that you can do is that stems from investigation of mineral inclusions in the olivine cores. These inclusions typically include garnets, clanopyroxene, as shown in one of the previous slides, orthopyroxene. So these are mantle phases. These are minerals that are stable in the upper mantle, but which do not crystallize in kimberlites and are actually resorbed by kimberlite melts. So if we sum these two pieces of information together, then I think we can safely conclude that olivine cores in kimberlites represent xenocryst derived from disaggregation of mantle rocks. And I'm not the only one to make this conclusion. This is quite well accepted in the kimberlite community now. However, this is a very important implication now. About 50% of olivine in kimberlites, 50% of the volume of kimberlites is made by olivine. And about half of this olivine volume is made by olivine xenocrystal. So in other words, the occurrence of olivine xenocrystal in kimberlites is a massive influence on bulk rock composition. And this is even clear in this chart, which is the first chart from the paper that I'm showing you today, where we have compared the magnesium silica ratio of multiple peridotites from a few kimberlites locality worldwide with the magnesium silica ratio of bulk kimberlite samples from those same localities, respectively on the x-axis and on the y-axis. As you can see from this chart, there is quite a there is quite a neat direct correlation between these two parameters. And this, of course, implies that the composition of kimberlite rocks is at least in part a function of the composition of the entrained mantle material. What, however, is unclear from this chart is whether we're only looking at a physical entrainment, whereby parts of the mantle are entrained in the kimberlite melt and therefore influence the composition of the kimberlite rock, or whether there is also something else. For example, assimilation could be involved. To address this question, I'm now moving on, and I'm going to compare the composition of olivine rims and the composition of olivine cores initially in a bunch of selected kimberlites. So on the x-axis we have the magnesium number, and on the y-axis we have nickel oxide. So first, here I'm plotting the composition of olivine cores in the grizzly kimberlites, which you can see are restricted to relatively high magnesium number, so above 90 essentially. And these are the rim compositions, where the magnesium number is relatively constant at around 91.5. Now I'm plotting the other end of the spectrum. So olivine cores from Kalgoorlie in South Africa, you can see a huge spread of olivine core composition down to magnesium number 78. And interestingly enough, the olivine rim composition are also displaced towards a lower magnesium number of about 87, 85. Then we have a third case, just as an example, Bulfontein, again in South Africa. The cores are a sort of an intermediate case, and similarly, the rims plot in between the grizzly and cavalli rim composition. So, as I told you before, from now on, I'm going to use the average magnesium number of olivine rims as a proxy for the kimberlite melt composition. But I'm going to do something a little bit bold. I'm going to take the average of the olivine core composition, the average magnesium number, as representative of the mantle wall rock composition. While this might not be statistically very meaningful, because of course we have to first be sure that before we do an average, that the data are normally distributed, this is just a good approximation of what is actually entrained. I'm also going to use the fraction of olivine with the olivine cores with a magnesium number less than 90 as an alternative parameter rather than the average magnesium number composition for the olivine cores. And I take this number as 90, this threshold, because olivine in the mantle usually has a magnesium number higher than 90. So everything lower than 90 has to be anomalous. So what we've done for this work, we have first compiled existing olivine major and minor element compositions from around the world, so divided them by core and rims. And then we have added data for 27 new kimberlite localities. As you can see from this from the map, most of the kimberlites are actually from Southern Africa. However, we also have a good representation of kimberlites from North America, Greenland, Brazil, Russia, and a couple of samples from India and Finland. I guess after I showed you the previous data, these two charts are probably quite predictable. So on the left-hand side, on the x-axis, there is the average magnesium number composition for olivine cores from every given kimberlite compared to the average magnesium number for the olivine rims of that kimberlite. As you can see, the uncertainties are quite large, simply because we're averaging quite an heterogeneous population of olivine cores. But regardless of that, the fundamental observation here is that these two variables are quite nicely correlated. On the right-hand side, the y-axis is the same, so the average magnesium number of the olivine rims, whereas the x-axis is the fraction of olivine cores that has a magnesium number lower than 90. There is a fraction of olivine cores that have an anomalous composition for the lithospheric mantle. And again, there is a quite nice correlation between these two parameters, which we also double tested with the student t-test and so on. Importantly, here we are not comparing the composition of an individual olivine rim with the composition of its own core. Indeed, as shown by this backscatter electron image, there is no correlation, no direct correlation between core and rim in individual grain. The correlation is across a kimberlite body. I'm showing you this image because I just want to make clear that there is no diffusional control whereby a rim composition is directly controlled by its own core composition. There's really not much diffusion ongoing here. What we are really comparing here are the composition of the kimberlite melt given by the average olivine rims versus the composition of the entrained mantle given by either the average core magnesium number or the fraction of olivine cores with a magnesium number lower than 90. Now, the question is, of course, what is giving us this correlation? And once we look at some petrography and some experiments, the answer is MANTLE, is assimilation. So we have indeed extensive petrographic evidence, as you can see, for example, from this image up here on the upper left side, whereby orthopyroxene to some extent, to a major extent, but also cyanopyroxene and other phases, including olivine, are resorbed in kimberlites. Here you can clearly see this resorption feature for orthopyroxene that seems to be beaten by the kimberlite melt that then crystallized the ground mass. A bunch of guys from Russia and elsewhere have done experiments where they've tried to put nicely hewidral gem-like crystals of garnet, orthopyroxenes, and cyanopyroxene inside a kimberlite melt, bring them up to a relatively high pressure and temperature, I think 1 GPa and 1400 degrees, and the result is that these grains are resorbed, meaning that kimberlites assimilate lithospheric mantle material during ascent. So the correlation that we found, that we observed before, is probably best explained by assimilation of lithospheric mantle material in kimberlite melts. However, this direct correlation can only occur if kimberlites around the world start with a broadly similar primary composition. Otherwise, if we assume that a range of primary melt composition occur, then we would not find a direct correlation once assimilation is included. What assimilation does is simply to move the composition of the kimberlite melt and therefore the composition of the olivine rim the composition of the olivine rim, so the magnesium number of the olivine rim, up or down this chart. The next question is that how does the assimilation model actually works? So I've done a bunch of mass balance calculations to really to try to pin down a little bit better the details of this process. And the interesting observation here is that if we assume that primary kimberlite melts have a magnesium number of around 84, just by taking what values estimated in the literature has jumped to, then we realize that the kimberlite melt composition at surface generally have a lower magnesium number than the primary melt. This actually means that when we assimilate lithospheric mantle material, the composition of the magnesium number of the kimberlite melt decrease. However, mantle peridotites typically have a magnesium number that is higher than 90. So in other words, if we assimilate lithospheric bulk peridotitic material with a magnesium number higher than 90 in a primary melt that has a magnesium number of about 84, maybe 83, maybe 85, then the magnesium number of the melt at surface should be higher. Actually, we don't see that. We see the opposite way around. The composition of the melt in equilibrium with the olivine rims has a lower magnesium number. So we cannot simply assimilate bulk peridotitic material. We need another process. There is enough literature about experiments done to understand assimilation in kimberlites, which tell us that assimilation of orthopyroxene can be the key. So here I have just reported two equations from Stone and Luth, a nice paper in 2016, where essentially they looked at what happened.
Okay. Yeah, let me see.
Just give me the green light when I can continue.
Okay.
And sorry everyone for the interruption.
Could you move back to the previous slide?
Yeah.
Yeah. I think, yeah. Let's go on. Yeah. Yeah, to the previous slide. This one. Yeah. Could you re-explain this figure and then moves on? I think then it should be a full story.
Okay. Yeah. So here I was at the point where essentially was proposed as an explanation for the former chart, an assimilation process for which we have extensive evidence both in the petrography, as you can see, for example, from this chart, from this image on the left-hand side, where orthopyroxene is clearly resorbed by the kimberlite melt that then crystallized the ground mass. And here on the right-hand side, there is an experimental charge where garnets and pyroxenes that were originally individual have sit in a kimberlite melt for a few hours, for actually an hour or so, and have been clearly resorbed. So in other words, we can explain this correlation between the composition of the kimberlite melt and the composition of the entrained mantle, assuming a single relatively homogeneous starting primary melt composition in the sublithosphere, and an assimilation process that shift the composition of the primitive kimberlite melt, or the composition of kimberlite melt that we see at surface up and down this chart by simply changing the amount and the actual composition of the assimilated mantle material. So to go into the details of the assimilation model, I did some mass balance calculations, trying to understand the actual process more in detail. So what came out from this exercise? So in this exercise, I first compared the composition of the magnesium number of primary kimberlite melts. This is estimated to be around 84 plus minus 1. With the composition of kimberlite melts that are in equilibrium with the olivine rims. What comes out from this exercise is that essentially all kimberlites, potentially with a couple of exceptions, have a lower magnesium number. All the kimberlite melts in equilibrium with olivine rims have a lower magnesium number than the primary melts. This implies that bulk assimilation of peridotitic material cannot be the process that is actually changing the kimberlite melt composition, because bulk peridotites have magnesium number higher than 90. So if we assimilate bulk peridotitic material, then the magnesium number of the primary kimberlite should increase. Whereas what we see is that the magnesium number of the melt in equilibrium with the olivine is lower than the magnesium number of the primary kimberlite melt. This means that we need to find another solution, and the solution is given by this set of equations that are from this nice paper of Stone and Luth in 2016. So these guys essentially trying to understand the reactivity of orthopyroxene in carbonate-rich melts, in their case in dolomitic melt. And what they found is that orthopyroxene react with the dolomitic melts to produce peritectic olivine and clinopyroxene and CO2. However, because clinopyroxene is absent in kimberlites, magmatic clinopyroxene, then they formulate the second equation whereby clinopyroxene further react with the dolomitic melt to produce more peritectic olivine and calcites dissolved in the melt together with CO2. So if we just combine these two equations, something quite interesting comes out. That is, orthopyroxene react with the dolomitic melt to produce peritectic olivine and calcium carbonate dissolved in the melt plus CO2. So what you can see here, and this is why I have circled in red magnesium, is that during this process, magnesium in the melts, in the dolomitic components of kimberlites, is actually consumed to generate more peritectic olivine. So by assimilating orthopyroxene, the kimberlite actually spends some of the magnesium budget, and this can explain why the kimberlites in equilibrium with the olivine rims have a lower magnesium number than primary kimberlite melts. That is melts in equilibrium with the mantle source. So the chart that I showed before also requires a relatively homogeneous primary kimberlite melt compositions worldwide, and regardless of the age or the geographic location of a given kimberlite. This is confirmed further by looking at the incompatible trace element patterns of kimberlites, which are remarkably homogeneous with some variability between locality, but overall the shape is remarkably homogeneous for kimberlites worldwide. And this once again requires that the sublithospheric source of kimberlites has to be fairly similar for kimberlite worldwide. So to sum up this first and more chunky part of the talk, kimberlites are hybrid rocks, which include magmatic components, olivine rims, carbonates, oxide minerals, mica, apatites, and the like. They also include abundant mantle fragments, including olivine cores, probably the most abundant of them, as well as diamonds, very little. They include crustal fragments, and hydrosoil morphases, which are often overlooked. Serpentine is the key player here, but also some chlorides and part of the carbonates have an hydrothermal origin. So it's quite simply, if you take a kimberlite rock, and analyze it, and powder it and analyze it, don't expect to get a kimberlite melt composition. This is, I guess, the bottom line. You need to take into account the entrained mantle material, the entrained crustal material, the assimilated mantle material, as well as the loss of volatiles, which necessarily occur during ascent. So I'm going to use the last few slides of this talk to say just a few words about what kimberlite melts potentially are and what people have thought so far about them and what I personally think. So in previous years, two very different approaches have been employed to trying to figure out, to nail down the composition of primary kimberlite melts. The first one is what I call the bulk rock geochemical approach, which was pioneered by Anton Leroux in early 2000. So Anton essentially analyzed the kimberlite bulk rocks from few localities and applied a range of screens to figure out crustal contamination. For example, here you can see a chart of silica versus gadolinium over lutetium, or silica versus magnesium. And crustally contaminated kimberlites have lower magnesium, higher silica, higher heavy rare earth elements, higher lead, and so on. Then he applied other screens to essentially either subtract accumulated olivine, so olivine that you find, olivine xenocrystal if you want, or add olivine that's fractionated. This is a chart of magnesium number versus nickel, again for bulk compositions. What he came up with is essentially an ultramafic melt composition with not too much silica, up to about 30%, but a lot of magnesium. These compositions are also very rich in water, have variable, not so abundant CO2, and are nearly devoid of sodium, which is quite a problem for any mantle-derived melts, because sodium is expected to be relatively abundant. If just following the previous lines, the previous part of my talk, it's quite evident that this approach has some fundamental issues. It doesn't take into account mantle assimilation. It doesn't take into account serpentinization. Indeed, not surprisingly, I think that this approach overestimates widely water, silica, magnesium, underestimate widely sodium. And importantly, these melt compositions can only be generated at extremely high temperature, above 1500 and probably around 1600 degrees. However, there is no evidence of thermometamorphism around kimberlite intrusions, meaning that these melts are not particularly hot, which of course goes against these estimates of primary melt composition. The second one is a completely different way to tackle the problem. It's what I call the melt inclusions approach that was pioneered by Dima Kamenetsky and other Russian colleagues. And essentially what Dima and others did in the past was to look at the composition of secondary fluid and melt inclusions mostly in olivine, but also in other phases in kimberlites worldwide. What they found is that these inclusions are dominated by carbonates, both dolomite, calcite, and magnesite, but also alkali carbonates, halides, alkali sulfates, and a bunch of other quite awkward minerals, especially for a magmatic environment. So they inferred that this secondary fluid inclusion trap an alkali-rich chloride carbonate melt component. And from there, they went on speculating that also the primary melt composition is indeed an alkali carbonate-rich melt. Well, there's a very basic and fundamental issue here. These are secondary inclusions, they're not primary, meaning that they trap a residual fluid, not a primary melt composition. It's a little bit as if you take granite, you look at the secondary inclusions in quartz, which are predictably full of enriched in saline fluids, and then from there you conclude that saline fluids are the parental melts of to those granites. Of course, you would never do that. Yet these ideas has gained quite a lot of momentum in previous years in the kimberlite community, to the point where kimberlites were assumed, primary kimberlite melts were assumed to be carbonate or carbonatitic melts, if you preferred. Kelly Russell, for example, developed this nice study in Nature in 2012, whereby carbonate melts on the way up assimilate orthopyroxene and bulk peridotite material, exhaust CO2, and so you have a very fast ascent driven by CO2 solution, and at the same time you develop these more silicate carbonate melt compositions that are akin to kimberlites in the upper crust. The problem is that if you try to do a little bit of mass balance, you need to, starting with a carbonate melt composition, so with a pure carbonate melt composition, you need to assimilate something like 40% of mantle material, which clearly pose some serious issues in terms of energetics, for example, in terms of capacity of this melt to go through the mantle and ultimately erupt. So a few years ago, we tried to develop something probably simpler, I would say. So a new approach to try to reconstruct the kimberlite melt composition, which is largely based on a state-of-the-art model analysis using backscatter electron images. So then we built up this equation that is much more simpler than it might look like. So the first component is just our model reconstruction. So it's the volume percent of magmatic phases. This MP here means magmatic phases. In other words, we are not considering all the olivine xenocrystal that you can see in these pictures. Then we multiply our estimates of the model from the model analysis for the density and the composition measured by electron microprobe, and to these we add a component. So we have two correction factors: one that consider alteration, essentially serpentinization, and the second one that consider the gassing. And then we also need to subtract the effect of mantle assimilation. I'm not going into any much details here because this is published and this is really not the focus of this presentation. But if you're interested, the paper was published a couple of years ago. So we tested this for just one locality in Kimberlite in South Africa, and we came up with a calcium magnesium rich silicate carbonate composition. So essentially something that is intermediate between the ultramafic melt composition proposed by Anton Leroux and the carbonate melt composition proposed by Dima Kamenetsky and then Kelly Russell and others. I must say that this is still a very incomplete procedure in that, for example, we are still not able to correct for sodium. There is very little sodium in kimberlites, mostly because there is no host for sodium. We haven't really found yet a way to correct for the fluid mobile elements that are lost on the way up, but we are currently working on it experimentally with a new project here at the ETH, new PhD project. Importantly, this silicate carbonate melt composition in terms of calcium, silica, magnesium, and major oxide compositions are comparable to what one would get from partial melting of a carbonate-bearing peridotite mantle below the lithosphere. So also this reconstruction seems to be consistent with a sublithospheric source of kimberlites, together with a plethora of other lines of evidence that I'm not really exploring in this talk today. So to conclude, I showed you today that kimberlites are very complex rocks. What we really don't know yet is what is the role of crustal fluid in reworking the petrology and mineralogy of these rocks. There is still a fair bit of work to do on this. I showed you that kimberlites possibly derive from silicate carbonate melts, so that the primary kimberlites are silicate carbonate melts, yet we still don't know the details of these melts in terms of volatiles, especially water, in terms of sodium and other fluid mobile elements. It is clear that kimberlites are heavily modified during transit through the lithosphere, yet we don't know exactly what is the extent of mantle assimilation, because that is largely dependent on the assumed primary melt composition. And finally, I think we can confidently conclude that kimberlites derive from a sublithospheric source, but we are still debating how deep is the lithospheric, is the source, whether it's as deep as the core mantle boundary rather than somewhere in the lower mantle, the transition zone, or the asthenosphere. And here, I think the opinions in the kimberlite community and elsewhere vary widely. So before concluding, I'd like to thank my former associates, postdocs, and PhDs of the Kimberlites and Diamonds Research Group in Australia, that unfortunately I had to leave behind by moving to Zurich, these students and postdocs were really instrumental in generating some of the data that I showed you today, and in general to bumping ideas and ultimately helping to generate the publication for which you have invited me. And also I thank to some of the sponsors down here, Petra, Mineral Services, De Beers, and the University of Cape Town to provide some of the samples and funding for our research. Thank you very much.
Well, great. And now it's time for questions from the audience. So when you ask a question, would you please first let us know your name as well as your institution. So also, you could also type your questions in the chatting section. So Tao, would you like to be the first one to ask, since you have already typed a question? If you could open your mic, you could go ahead and ask a question.
Here's the chat. Okay, so the question is typed there.
Yeah.
You said that those kimberlites might have experienced hydrothermal alteration or serpentinization, especially for the olivine rims. I think that kimberlites could exchange magnesium with water to a certain extent. True. Thus, could the constant magnesium number values of rims be the results of equilibration reaction with hydrothermal alteration or serpentinization by interaction with water? So there is a paper that is just out in Journal Petrology that is from one of my PhD students, where essentially we show that there is a specific type of olivine that equilibrates with these hydrous fluids and indeed is in equilibrium with serpentine and even has inclusions of serpentine. This is essentially pure forsterite, though. So it's completely true that these hydrothermal fluids can equilibrate with olivine, but they generate a very specific type of olivine that is not the magmatic olivine you see there. So those are not the nice hydral rims that overgrow the olivine cores. The next question is from Rong Shu. If derived from a common mantle source, what is the isotopic composition, FOSO? I have a, I was supposed to present at Goldschmidt's earlier this year about this work. I think that the ancient and deep mantle source of kimberlite is indeed FOSO. But I mean, I should bring up other slides that I didn't, I might have somewhere hidden, but that's quite a long talk, a long conversation. So maybe you will hear back from me once this paper is published. It's currently under review. I think it's FOSO, yeah. But it's much of a longer conversation than this.
More questions from the audience?
Oh. So another question from Rong Su. Can carbonatite melt assimilation in the asthenosphere produce primary carbonated melt? I think here there is a little bit of confusion with the terminology. So primary means that is a melt when it leaves, that is in equilibrium with its mantle source. So essentially, after that melt leaves the sorry? Okay. So after the melts leave the source, then it's not primary anymore because it starts to interact with the mantle and potentially assimilate something. So I think if maybe you meant the opposite way around. Essentially, if a primary carbonate melt can produce carbonatites, or otherwise I'm a bit confused.
Yeah, I agree with your interpretation.
Yeah, you know, once a carbonate melt starts to assimilate lithospheric, any mantle material, also asthenospheric material, its silica content will increase. So you will progressively move towards something that is more kimberlitic before assimilation in the lithosphere. Yeah, I mean, it's possible. It's possible that part of the assimilation already occur in the asthenosphere, though it really depends where you want the kimberlite melt, or in general your carbonate melt formation to occur. I think that at least a bunch of us who are actively working on this topic think that the extraction of kimberlite melt assimilate at some sort of a rheological boundary, so most likely the lithosphere-asthenosphere boundary. If that's the case, then you don't really have much interaction with the asthenosphere because you are already out of the lithosphere, out of the asthenosphere pretty much when the melt is produced and migrates away. So imagine if you have a thermal and upwelling, like what you would call a plume, that impinging at the base of this very thick lithosphere, then if you have low degree partial melting there, that's when you would produce a silicated carbonate melt. We can call it a carbonate melt, we can call it kimberlite. And then essentially the melt would start to ascend straight into the lithosphere. So this is currently my preferred scenario. But you know, you might argue that kimberlite melt formation occur a little bit deeper, so just above the metal saturation curve, for example, due to carbon oxidation. And then in that case, yes, the melt would go through some 50 or 100 kilometers of asthenosphere, And yes, some reaction would occur, for sure.
Okay, more questions from the audience? Natasha, do you have a question?
Yes, I actually wanted to ask one about the Russell paper you've mentioned. You told that it is not, I'd say, good because it has issues with thermodynamics. And I wanted to clarify which ones. I just thought that this process is quite, it doesn't reach equilibria in general. So it moves as fast as, I don't know, it is possible. And the reactions don't reach equilibria while this in this ascent is happening.
Yeah. So the problem is not really with the model per se, because even if you have a silicate carbonate melt rather than a carbonate melt, and that silicate carbonate melt react with the lithospheric mantle, it would still produce CO2 as a gas phase or as a fluid phase, not really as a gas. That would help the ascent. The problem is that if you want to start with a pure carbonate melt that has zero silica or just very little silica, first of all, it's very hard to make such a melt in the mantle, and second, if you want to start with that composition, then to get to a silicate carbonate melt composition as we see at surface, you need to assimilate something like 40% of lithospheric mantle material. So it's not a thermodynamic, you can see there's a thermodynamic problem, but it's really a problem with the energetics. So you don't have sufficient energy to assimilate so much lithospheric mantle material. That's the problem. Even though you are under these equilibrium conditions, for sure, yeah.
And if we are using, for example, material that is enriched in orthopyroxene or something like mantle transition zone, I don't know, wouldn't it be more energetically, I'd say, okay? No?
Can you try to phrase the question?
Yeah, okay. Well, I mean, if we need to move through a certain zone that is enriched in this material, and we don't have to assimilate a lot of lithospheric material. I mean, there is not much of orthopyroxene in lithosphere in general. So this is why we need to assume a lot of material to get this silica and stuff. But if we are going through a certain zone that is enriched in a spot, let's say, that is enriched in this material, and so we need to consume less less of the area, wouldn't it be working, this process?
The problem with the mass balance remains, because even if you say, well, most of the lithospheric mantle is danitic and there is 5% orthopyroxene, and then you have pockets of orthopyroxenites. Okay, this is just an extreme end member scenarios. We know very well the lithospheric mantle that is entrained by Kimberlite, how it looks like, because people have studied those xenoliths for something like 40, 50 years. So we know that there is roughly between 25 and 30% of orthopyroxene. Even if you assume that you only go through pockets of orthopyroxenite and that's only where you start interacting, you still need to assimilate something like 35–40% of that material. And so the problem remains. So you can still do it. You can still do this process as long as you start with a melt that already has something like 20–25% of silica. And then, I mean, you, of course, you still assimilate some of it. You probably move your silica contents up of maybe 5%, something like that, if you assimilate, I don't know, 10% or so or orthopyroxene. And still you're bubbling out your CO2, you're producing your fluid. That enhance the the ascent of kimberlite. At the same time, I mean, I think the model of Kelly-Russell works for some kimberlites, but I don't think it works for every kimberlite. We have plenty of kimberlites that are dikes, that don't undergo any turbulent ascent. So all the olivine is not fragmented, all the olivine is nice individual. In that case, I'm not really sure there is so much of CO2 exsolution ongoing.
Mm-hmm. So okay, yeah. I see. Thank you.
Pleasure.
Okay, one last question.
Yeah, very general question from Luke. Kimberlites carry super deep diamond, but kimberlites need the cratonic root to form a wrap. So do we have a sampling bias of super deep diamond? Can we expect super deep diamond being brought up to lower level by plume, but not sampled? Good on you, Luke. If I had the answer for this, the definitive answer for this, I mean, that would be already in Nature. It would be published in Nature already. So we have a fundamental problem in the kimberlite community, whereby we know that those diamonds come from very deep. Many of those diamonds are not retrogressed, so the inclusions in some of those diamonds are not retrogressed, meaning that potentially those diamonds have to come pretty much straight from, let's say, the transition zone up to the crust. Many people don't think that is possible. Many people think that those diamonds have been transported, as you write here, by mantle upwellings, call them plumes, or simply by mantle convection to the lithosphere-asthenosphere boundary, and that's where they are ultimately entrained. I honestly don't have a definitive answer for this, but if I have to deal with the experimental petrologists who tell me that carbonate melting cannot occur any deeper than 250, 300 kilometers, unless you have massive perturbation in the oxygen in the redox, then I think it's the most likely answer is that yes, those super deep diamonds have been transported to the lithosphere-asthenosphere boundary by mantle convection or plume activity. And that's where then you have your plumes that actually oxidize your carbon, and you have carbonates melting, and ultimately kimberlite extraction. So that would be at the LIB. But this is my current thinking, and other people, I'm sure, in the kimberlite community would think differently. Oh yeah, and there is a sampling bias for super deep diamond. So you see a lot of these studies about super deep diamonds, but they actually come from very few localities. So not all kimberlites have super deep diamonds, but a few do have quite a few, quite some. Yeah.
Okay. Thank you, Andrea. Thank you again for your talk, as well as the interaction with the audience. Although it's I think it's the first time that I see most of the questions interacted by typing, other than opening the mic. But it's a very unique experience, and I do understand that some of the students, they are still in their office, that they have to share office with other people, so it's inconvenient for them to open them. And look at his kids.
Yeah.
So that's why. Okay, I think it works. I think the online press and the seminar is great for that purpose. That makes at least convenient for people. Okay, great. Okay, thank you very much, Andrea. Have a good day.
And thank you for staying up for this. Bye-bye.